Started recording?
Yeah, yeah.
Huh?
Yeah.
Okay, fine. Okay, welcome everyone. Today I am going to talk about a very common topic, but some kind of advanced topic, that is a comparison between LED and a laser. I guess you all guys have done your semiconductor device classes, so you guys know about the basics of the band structure and all those transitions of the electron and hole in terms of the band energy band diagram. So if you know that thing, so this will be a bit easier, and I will try to focus all my conceptions in terms of those energy band diagram. Okay, so first of all, in this presentation we are going to first look at the basic band diagrams, then we will discuss some review of the emission of light, how we can use the energy band diagram to model the emission of light. Then we are going to give a brief introduction to the LED and laser, and after that we are going to discuss some of the comparison of these two optoelectronic devices, so that you can make your choice in terms of application in future. So where you can use these, whether you have to use the LED and the laser, because sometimes it becomes arises some confusion, because they both are light emitting, right? LED is also a light emitting device, laser is also a light emitting device. So should we use the laser for the lighting of our houses? Can we use that? Will that be helpful?
No, if you make use of the laser, it will be much more costly.
Costly and also harmful also.
Okay, no, okay, the costly term is okay, it is costly. Harmly, you cannot make the low power lasers, so that will not be harmful at all. Okay, if you just make the laser in the correct wavelength, that is not harmful for your skin, that is perfectly fine. But the point is it visible? So that's what we are going to discuss, and at the end of the class I hope you will be able to answer this question of mine. Okay, next, the review of the band diagram. We all know the energy band diagram, all the materials that have a valence band and a conduction band, and the position of the valence band and conduction band defines whether they are metal, semiconductor or an insulator. In metal, we know the valence band and conduction band are overlapped, so that there is always a availability of electron, and in the conduction band, so you get always a conduction. In the insulator, the band gap is so high that the electron cannot go up to the conduction band, so that you cannot get any current. So that's why this is called insulator, no current. And the semiconductor, it has a band gap, moderate band gap, so you can engineer that band gap and use that material as for different application. That's what we are going to do for the LED and lasers. So now, what is the emission of light? So we know in the thermal equilibrium there are some electrons in the conduction band, and sometimes what happens, some of the electron relaxes down to the valence band and emit light, and the wave energy of this emitted light is equal to the difference of the energy of the conduction band and the valence band. Okay, so this emission can be classified into two types. The number one, that is spontaneous emission, and number two, that is stimulated emission. The spontaneous emission is when the electron jumps from the conduction band to valence band at his own will. So without any external perturbation, just it happens naturally. That is the spontaneous emission. So it will emit light. We just say is equivalent to one photon. So it will emit a photon. So, but what is stimulated emission? Stimulated emission is one photon comes and it excites another electron who relaxes down to the valence band, so that at the output we get two photons. One, the incoming photon, and the one that emits from the relaxation of the electron. So for in this case, we are having an incoming photon and two outgoing photon. So that means we have some gain when we are talking about the stimulated emission. And also there is a phase matching, because the incoming photon is stimulating the another electron to relaxes. So the two outgoing photon has the same phase difference, or we can say they are in coherent condition. Now, what is LED? LED is actually a normal forward biased PN junction. It's nothing else. So what we do, we take a normal PN junction. If we apply a certain bias, the current will flow, the carriers will flow, and when the carriers flows through the junction, they get recombined. And this, the previous slide I have shown the relaxation of electron. This is actually recombination, right? The electron and hole are recombining and emitting a photon. So LED is actually driven under the spontaneous emission of light. So actually, the emission of the LED is a spontaneous emission of light. So what is the here you can see when you are forward biasing, the lights are emitting from all directions. So the point here is, as is emitting from all the directions, you will not have an equal phase, so that the emitting light will not have any coherence in the output photons. So that's why it will have a divergent beam. Okay, so here is the example. So what are the possible applications for this? So as it is diverging, you can use it in terms of many applications, right? You can use it as the light, you can use it as a different source, you can use it as the detector, because if you have a certain wavelength, you are emitting that light, you can just sense that. So you can form different, and it also has some various kinds of biomedical applications and some all sorts of everywhere there is LED. Even in the screen of our television is LED, because it gives a very precise wavelength of light that gives a very pure light. Okay. So now, a laser is one kind of semiconductor material that has two mirror on this both sides. You can see from this cover, here is a reflector and here is another reflector, and in between there is a semiconductor device. So in this laser, we just somehow generate a spontaneous emission, and that photon will just move to and forth into the semiconductor and in the reflector, and it will just emit a huge bunch of photons. So that's why you will have a very big gain. So just by designing the cavity and the material, you can have a very big gain and a very powerful light in the output. So this is stimulated emission of light, and two important characteristics of the output beam is, I already said that this is, as it is the stimulated emission driven output, so the output will have a very coherent, the photons will be in coherence, and it will be very directional. We see in the previous case the LED was not directional, it was just divergent, it has a very divergent beam. But in the case of a laser, it will not have any divergence, because what you are doing, you are just controlling it. You can see it from this figure, right? LED is a very divergent. You can see if you just look closely. Even you are very close, you will see a very divergent light. But see, that's a very laser light show, where the light is very directional for a very long distance. So that's why you can use it for when you want to directional a light for a very long distance, you have to use the laser. Can you name any application for that?
Laser, like if you want to make use for one guy giving a big song concert and all.
Yeah, exactly. For the lighting purpose. For scientific purpose, you can use it for the measuring of the very long distance, and for the laser is also used for the velocity of the
oceanic depth, right?
Yeah, exactly. This kinds of thing for where you need a very directional light.
And they're using oil and gas.
Exactly. So this laser, yeah, exactly. The direction of the oil and gas. If you just put that directional light, you will get. If you just kind of use that divergent beam like LED, it will just divergent, and you will not get enough information from that. You got that? So here is another the output characteristics. It has a divergent in terms of the lambda, but you can see it has a very specific lambda. It is monochromatic in case of the laser. So here is a chart of the comparison of the LED and the laser. So you can see the output power in the LED is very low, but output power in the laser is very high. But you can control that easily by designing the cavity, right? You can also have some low power lasers, but that will not be very feasible in terms of the cost. So here you can see that reliability for the LED is very high, but laser is not that much high, it's moderate. The cost is low, but for the laser is high. So you can see both have some good points, positive sides, and some negative sides, but it depends on your application. Okay? So can you just tell me at this end of this is my last slide of the presentation, can you just tell me